Welcome to this video on torque and the cross product. In this video we're going to be focusing primarily on the idea of the cross product as it applies to a torque situation, and we're going to try to make the cross product more physical rather than just some abstract mathematical concept, and we're going to do that with a couple examples. So let's jump right into it and take a look at this door as seen from above. So it's a little bit strange to look at a door this way, but you could think of the hinges being over here where the circle is, and they're stacked on top of one another, so we can't see the hinges at the bottom or the middle of the door. Over here we have the door handle, and the door could swing back and forth like this. Okay, now in the last video we set up the basic concept of what torque was, and so I'm going to start there as a very quick review, and then we'll jump back to this door example. We used the Greek letter tau to represent the value for torque, and that value looked something like a fancy T, and we said that if I were to push on an object, so let's say I apply a force right here where the door handle is, and let's say that force is 100 newtons, just for example's sake. Now let's say I, instead of pushing on the end there, decide to rather push over here, and we push with the exact same force over here. Okay, we would say that the value of the torque is different because of that. So we showed that the harder you push, the more the door rotates. So when I think of torque, I think of the ability of a force to rotate. So the ability to rotate. Now, that's not the best definition of what torque actually is. Another way you could think of it is the rotational ability, or the rotation of the door. So we would basically, if we were comparing these two situations, we would say that pushing with 100 newtons of force at this position, and I'm going to label the position as from the axis of rotation. This is the hinge over here. So the hinge of the door is serving as the axis of rotation. And what I'm going to say there is that applying a force at that position would give me better or larger rotation than applying the force at this position. So I might describe the position as this distance from the axis of rotation to where the force is applied. Let's call that position 2, and we'll do this one on the way out here as position 1. So I would say that the force is the same in both examples here, but where it's positioned is different. And so we had established the fact that R needed to be factored in to figuring out what the actual rotation of the object was. Now, another way we could compare these two situations would be to say, well, let's keep the R value the same. So we'll keep where we push the same, but I'll change the value. So the first value I will say is 100 newtons, but let's say the second experimental value, let's say I pushed with 200 newtons. Well, if you push the door harder, it's going to rotate more, which I think makes a lot of sense. So we're keeping the position the same, but we're pushing harder. So we can see that there's a direct proportion between these two and a direct proportion between R and F. Now here's where the cross product comes in. And the cross product is maybe one of the most confusing parts of torque for students, but it's really not that hard if you think about it in a very physical way. I'm going to get rid of the changing values of force. I'm going to say I'm pushing with 100 no matter what. But now what I'm going to say is, what if I pushed at an angle like this? And I'm still going to say that this F2 is still 100 newtons. But now I'm pushing on the door, so I'm still making contact with the door handle, but I'm not pushing directly onto the door. I'm pushing at a little bit of an angle to the door, and you could measure this angle from various different places. So the position at which it's being pushed is the same, so R is not changed, so that's the same. The magnitude of the force by which I'm pushing has not changed, but I would get a greater torque in situation 1 than I would in situation 2. So I would say that the torque in situation 1 is greater than the torque in situation 2, even though I'm showing that the force I'm pushing with and the position I'm pushing at on the door are exactly the same. So what gives? Why is that happening? Well, if you think of it from the physical perspective, here all of your push is directed into the door. In this example over here, not all of the push is directed into the door. Some of that force is directed along the door. So if you were trying to say what's the difference between those two situations, I would describe it as how I'm facing the door. Am I pushing all of my force into the door, or some of my force into and some of it kind of along the door? Okay, it's a little bit strange because we don't really think of things this way, and our wrist bends so that our hand is always going to push onto the door in the same way, regardless if we change the angle. So let's take a look at what's actually happening in this situation. If I look at the force 2, I could draw components to that force. I could say that there's this component, which might call the perpendicular component to the surface of the door, and then there's this component, which I might call the parallel component to the surface of the door. So there's two different components to this force. Now, in looking at force 1, I could say that the perpendicular component of the force is the only component that's present because there is no parallel component. But in both situations, what are we measuring the angle of the force relative to? Well, you might say the surface of the door, and in this example, that is true. The difference in angle here is measured relative to the surface of the door, but it's actually measured relative to this position or this length r. Okay, now those two things happen to be the same thing in this example, and that's why we can say the angle is measured relative to the surface of the door, but it's really measured relative to the length of where the force is applied relative to the axis of rotation. And we'll see in some examples why that can be slightly different where it's not the same as the surface. So in this example, they just happen to be the same. So when I'm going to pull the vectors out here separately. I'm going to say, here is this r vector, and I'm not drawing a direction on it yet. And then here's this f vector that looks kind of like this. Okay, so this was f2. And there's some angle between them. So I pulled out the door here. The door is no longer part of this scenario. It's just this r vector and this f vector. Now I'm going to put them tail to tail. So I'm going to say there's this r vector and then there's this f vector that's pushing this way. Okay. So now it looks kind of weird. It doesn't look necessarily like this picture anymore. But try to imagine how this vector and this vector lay onto the picture. So we've done it in 3 stages. We took it from this realistic stage to this stage where I pulled the door example out, but the arrows, the R value and the F value are still pretty much where they are in the picture. And now all I've done is I've shifted this arrow over to the right. So this is that R vector. And then I've shifted this value up so that the ends of the tail are joined together. This is the angle that I'm actually concerned about. And that's the same angle as this, and that's the same angle as this. Okay, so in the physical situation, the surface of the door and the angle to the surface of the door, right, is the physical angle. And here mathematically, the angle is still that same physical angle, except now I'm looking at it in terms of the two vectors rather than as the angle between two actual physical things. Okay. I know that's a little strange, so you might need to reverse it and watch that again to let it click in your mind. So looking at this example right here, What the cross product says is, take one of your vectors, we'll call this one r, and multiply it by the magnitude of f, but only the part of f that is perpendicular to r. So here's f2, which we said is 100, but now I'm only going to multiply by the perpendicular component of that vector to r. So this would be f2 perpendicular. So in essence, what I'm saying is, ignore the parallel component that lays along it. That would be the dot product, right? So here we have this cross product where we're saying only multiply the perpendicular component of one vector and the entire measurement of the other vector. So I'm measuring them relative to one another, not both relative to some absolute point. So I'll say that again. I'm measuring the two vectors relative to one another rather than measuring each of them to the same absolute 0 point. For instance, if I had shifted f2 and r like this, I would still say that the angle between them is exactly the same. If I was saying that I had an absolute 0 here along the horizontal, and I'm going to redraw it over here, these two angles individually might have changed, but the angle between them is still the same. And that's what the cross product is focusing on, as well as the dot product, except you're looking at a different component. We only care about the situation where the vectors are angled relative to one another, and then we're multiplying those two components. Now, another way you could look at it in this exact same situation is you could say, instead of leaving the r vector the same and finding the component of the f, I'm going to leave the f the same, and I'm going to find the perpendicular component of the r, which, if you think about it from this perspective, right, I would need to draw a component that is perpendicular to the f vector. So I can draw it on this side or on this side, okay, but I'm going to draw it over here on this side, and I'm going to show that that is the r perpendicular component. These would both give you the same solution, essentially, even though I've looked at one being the fixed one and the other one being the perpendicular component. So that's the way that I oftentimes will think of a torque situation. Am I going to keep the r value fixed and multiply by a component of the f value, or am I going to keep the f value fixed and multiply by a component of the r value? And that is just up to you. To me, the easier way to do it is usually this way. Keep the r value fixed and multiply by the component of the f value. Now is to actually put the number to this. So if you think about, if this is the angle in question, and I want to multiply by the perpendicular component of the f value, so that would be f2 perpendicular, that would be opposite the angle that's shown, which this value then would be the ratio for the sine of the angle between the two vectors is equal to the perpendicular component of the force over the total force. So therefore the perpendicular component is equal to f sine theta. But it's not just f sine theta with some absolute 0 position. It's f sine theta where theta is the angle between f and r. So when I do this cross product, what I'm going to say is tau is equal to f r sine theta. Theta being the angle between f and r. Now it doesn't matter if I write it this way, nor if I write it as f sine theta times r, because multiplication is commutative. So the fact that the sine theta is at the end here just goes to show that it doesn't matter which one of these it's paired to, you'll still get the same answer. So to wrap this video up, since it's a little bit longer than I usually give, we'll say that the torque is equal to, so the rotation or rotatable ability of the object is equal to how hard I push to rotate the object times where I push relative to the hinge or the axis of rotation of the object times the sine of the angle between where I push from the axis of rotation to how hard I push. So you could write it this way, or F cross R. Now, because the result here is a vector, this is going to have a direction, but we will only talk about that a little bit later when it actually has more impact on the physical situation.